So I have this difficult task of keeping you guys awake after such a sumptuous dessert, right? I'll try my best. I would say challenge accepted, frankly. So another bit of news, I am no longer with AIG, recently moved out of the organization, though, I would be heading the data product in one of the BFSI teams, but we'll see which one. That news is still to be broken up. Okay, so the idea here is to, I know since morning you guys have been going through pieces of data science, ideas, visions, implementation, and things like that. And what I wanted to do is very quickly take you through a story of, how do you productionize a data product, and this is an end-to-end journey. But before that, if you have been in this area of data science for as long as I have been, you would start seeing some irony which pops up every now and then. And for that, I keep on kind of blabbering on LinkedIn sometimes, and which is, you might be a data scientist if. And this is just one of the quotes of, you might be a data scientist if you believe natural language processing is a part of artificial intelligence. Now go and figure that one out, right? So coming back, what we will do is very quickly take a look at the business case on how do you convert a business problem into a data science problem to begin with. And once we have a data science problem, then obviously we go ahead and solve the data science problem. But that is where the real problem begins. The challenge is once we solve it, we still have to productionize it. The production challenges are very, very different than the theoretical challenges of solving the data science problem, and that is something which I'll also talk about. So this talk would be set in these three stages. So just to quickly set up the context. So, one of the problem statement which I'll pick up is a problem statement coming from the insurance industry. Typically, what happens in an insurance industry? What happens is you have, what you are assessing is risk. And once you assess the risk of a group of policies, then you can decide what premium to charge, right? If some of those risks, culminate into damages, then you pay the claim. And, sometimes what happens is some of these claims may get into litigation. Why get into litigation? Because of multiple reasons, right? So there might be a fraudulent claim. There might be a claim which is outside the scope of the insurance policy and multiple other things. And so you go and litigate, and the insurance company and the policyholder fights it out, right? So, once a policy gets into litigation, what happens is the team which is assessing the risk, do not get any data from the litigated piece. Why? Because anything and everything which gets into litigation now becomes privileged information. It can be attorney-client privilege. It can be PII-related privileged information, personally identifiable information, or it can be medical-related privileged information. And so the legal operations team would typically come in, and they would say, hey, you know what? This data is now mine, okay? Nobody else has access to this data. The challenge is, if the commercial insurance teams do not have access to this data, they cannot update their risk models, okay? So there is a huge problem statement here. And so, there are triangular stakeholders. There is a commercial insurance team, there is a legal operations team, and then the science team comes in there. Why do they come here? They come with a mandate that, can you accurately predict which part of data contains privileged information? If you can predict that, then what I will do as a legal team, what I'll do is I will redact all the privileged information and give away the non-privileged information back to the commercial insurance team. As simple as that. Okay, so just to recap, there is a team which needs data, there is a team which can't share the data, and then there is a third team which comes in to enable, to bridge the gap between all of them. And so what happens is, let's just understand, because this is an important piece of the puzzle. What we want is, we want to convert this problem into a data science problem before we start solving, right? So this is a purely business problem right now. And remember, what we asked, the ask was, can you accurately predict the parts of the document, the parts of text document which contains privileged information? And once you have that, then we can go ahead and solve it. And at this point of time, what happens is, the question is, what is the, what is the right number we are predicting? So, we sat down with the legal team and said, hey, you know what do you think is the right accuracy number you want to have? And after a few deliberation, it's like, anything about 90% would be a good number. So, if we can predict with 90% accuracy that the data is privileged and we remove that, good to go. There can be some leakages. Fair enough. So here, the challenge from the data science perspective is, the data was highly skewed. The data was so skewed that the positive class, which is the privileged information, is only 6%. Non-privileged information is 94%. So if I just go ahead and say everything is negative class, everything is non-privileged, I'm still 94% accurate, right? And that is where we were looking at a blank screen. We had no idea what to do. Everybody is scratching their head in the conference room, have absolutely no idea what to do, till the sun rose again. Okay? Okay, so how did the sun rise? So the challenge here, what we decided to do was, the way we found the solution was in the broken limb. How? So as we, the data scientists, started looking at the data, we realized there were anomalies in the data. There were cases of broken limb where the lawyers and paralegals, in some cases, have called it as a privileged information, meaning positive class. Their contention is, it is still a medical-related injury, and that is why it should be positive class. Then there were some lawyers and paralegals who were saying, it is such an obvious thing. Broken limb, it's visible, it's obvious, and it should not be called as a privileged information. So they disagreed. And this was the epiphany moment. This is where we reached out to the legal team again. Hey, you know what? Your lawyers and paralegals, when they are tagging the data, they disagree on this. What do we do? And so these guys were like, if in 80% of the cases, if lawyers and paralegals agree that this is a privileged information, we call it a privileged information. If it is not, if they disagree, then we call it a non-privileged information. And that was the epiphany moment. That was like, voila. What you are looking is not accuracy as a metric. What you're looking at is recall as a metric. And just to explain to people, obviously recall is very difficult to explain to lawyers. And so we took cases of, for example, Google search, that if top 10 search results come in on the first page of Google, when you search with a key phrase, if 8 of those top 10 results is something which is relevant to you, then your recall is 80%. And this was a very, very clear, good way of explaining to them, coming down at their level and explaining things back, and which was very evident. And they said, in the court of law, if you can say 80% of the time, if my recall is 80%, I can defend it. Perfect. And that is how we converted a business problem into a data science problem. Now, the second part, we have to solve the data science problem. And so you start building, typically how you would do. You start with a baseline code. And the baseline code is a very straightforward NLP implementation. It's a classification algorithm. It's a supervised learning classification algorithm. You have a positive class. You have a negative class. Yes, they are highly, this is highly skewed. There are ways of getting around the skewness of the data. And you take into consideration on all of those things. So you start with, for example, just a quick refresher on people who are relatively new to NLP. What you do is, the first step is tokenization. You take the entire sentence, words, phrases, and tokenize into at a word level, typically. There may be by n-grams, which is so this tokenization is called bag of words. So every word can be put in a bag and basically be called as a feature vector. Then somebody say, so if the sentence was, the cat sat on the mat, and if I'm doing tokenization, so the would become a token. Cat would become a token, sat would become another token, and so on and so forth. So then somebody can say, hey, did the cat sat on the mat, or the mat sat on the cat? Because by doing bag of words, you are losing context. And yeah, that is true. Let's do bigrams. So the cat sat, and then somebody can say, hey, bigram is still not capturing, so trigrams. And till the time you get into a problem of dimensionality problems and things like that. But that's a good approach. The industry swears by it. Then you have what you want to do is build word classes. Word classes is, for example, email IDs, right? Everybody's email ID is different. But you still have, what you want to do is you want to replace the email ID with a token, say __ email ID __. And what that does is it is a representation of the email ID occurring in the entire phrase. And what that does is it improves the word transition probability, because my email ID is different than somebody else's email ID, and that is why the word transition probability would be very, very low. And so the email ID is just one thing. Maybe dollar amount can be another thing. Telephone numbers can be another thing, and so on and so forth. You want to augment the data with new dictionary sources. So for example, here, what we would have is we would have a list of all the lawyers who would typically reach out to, these lawyers would typically represent the organization in case of a litigation. So you have a list of, let's say, 1,000, 1,500 law firms. And so, what you have done is looked at all the email IDs and said, okay, this communication comes from a known lawyer or our lawyer. Or, the other thing can be a telephone number with an extension. So typically a telephone number with an extension might belong to a law firm or a doctor and things like that. So those are some good ways of increasing, the value of your feature vector, and while adding, keeping in account, while enriching the feature vector discriminability. Now, the baseline model, a very good baseline model is obviously logistic regression. What we also did was we built, support vector machines and random forest. So two totally different areas. One from fairly this thing, and then the random forest part is more decision tree based. feature evaluation. Once you have a baseline system, you want to look at which features are most discriminative, and if they are discriminative, why they are discriminative. And that would help you enhance your feature vector and build stronger models as you go along. Okay? And so this brings us to the productionization part. Once you do have a model which has reached the 80% recall, and in our particular case, the random forest model actually exceeded the 80% recall, but what we end up choosing was support vector machine model because of the evaluation complexity. So during evaluation, support vector machine only has a complexity of ON, meaning what you do is just you take a quick dot product of the support vectors multiplied with the feature vector and sum it up. It's as simple as that. Whereas the evaluation complexity of a random forest is very, very large. It's n log n, and so it cannot be done real time. So here is a very good example of even though in practice, in academic efforts, your algorithm might have much better performance in certain cases, but when it comes to implementation, you might have to take a call in terms of which process to follow, and there can be multiple other this thing, and this is what I'll talk about as successful technical decisions. So typically in all the data products which I have been part of, I have realized that there are few principles of sort which help you definitely achieve what you aspire for. So things like modular architecture. You don't really want to tie yourself down to an architecture, be it an open source architecture or a closed source architecture, and later realize that I am so deep down tied up that I can't get out of it. Component communication, very, very important. Each modular component should be communicating with the other modular component through APIs. Very, very important. And why do you want an API? Because of distributed computing, as well as failovers and multiple other reasons. Flexible topology. Sharding at a vertical level or at a horizontal level. You want to have something which can be scaled as your product is scaling. And it's very common in today's world to that business aspires for something which has to be in production very quickly, is running in real time, and has the ability to scale up as and when the consumers start using it. And sometimes when you are planning the product, it becomes very, very difficult to kind of look into the future in terms of what can be the scale eventual. Simple configuration. Everything should be, you should have a configuration file or a configuration web page where every single component can be configured. Model latency, something we talked about, and then obviously most important is the team, because without a good team, can't do much. I still have 1 minute, 30 seconds, but before that, I would like to say achieving a potential impact for up to $100 million by enabling new areas in an $8 to $10 billion market, very, very common, very easy to do. If you just take a small piece and build something new. Trying to disrupt an existing system takes much, much longer time. Build something new, and it's like a honeybee, right? You build a honeybee comb, honeybees will start swarming in. That has been my experience, definitely. So before I leave you, you might be a data scientist if your child's first words are deep, data, and model. And you can reach me at my LinkedIn profile as well as my email ID. We still have, I guess, 30 seconds if there are any questions. Great. So I did manage to make you guys sleep, huh? Great. Thank you so much.